Hello, everyone, and welcome to today's webinar, Improving Phosphorus Use Efficiency with RhizoSorb, presented by Phospholutions, a company founded in 2016 to enhance the efficiency of global phosphorus use. I'm Larry Elward, the custom content editor for Meister Media Worldwide, the publisher of Crop Life magazine, and I'll be moderating the webinar. Traditional phosphates can quickly tie up in the soil. In this webinar, you'll learn how Phospholutions' RhizoSorb technology reduces phosphate tie-up and improves soil anionic exchange capacity to improve phosphate availability. RhizoSorb is the only patented technology that is embedded into the fertilizer granule that reduces a grower's cost per acre while maximizing margins for retailers. This webinar has been approved for 1/2 CEU credit in nutrient management from CCA. To receive credit, you must watch the entire webinar. A QR code for reporting your credit will be provided at the end of the webinar. You simply scan the QR code and submit it. We'll also have time for questions at the end of the webinar. If you would like to ask a question anytime during the presentation, just type it in the question pane at the lower corner of your screen and click Submit. Questions will be addressed at the end of the presentation. Before we begin, I'd like to introduce our two speakers. First is Hunter Swisher, the president and CEO of Phospholutions, which he founded prior to graduating with his Bachelor of Science degree in Plant Sciences from Pennsylvania State University. Under Hunter's leadership, Phospholutions has raised over $18 million in venture capital to develop technologies to improve phosphorus fertilizer efficiency. Recently, Hunter was recognized in Forbes 30 Under 30's 2023 Social Impact class. He is the co-inventor of 4 patents pending around the world. Also speaking is Craig Dick, the Vice President of Sales and Marketing for Phospholutions. Craig recently joined the company to help them commercially launch the RhizoSorb technology to the American agricultural market. Craig has more than 2 decades of experience in ag tech business development, sales, and agronomy. Now I'm going to turn it over to Hunter to begin the webinar. Hunter?
Thanks, Larry. Appreciate it, and thanks everyone that's tuning in here today. We're going to go through a little bit here about the company, spend some time talking about phosphorus, and then get into a little bit more about the technology. To start off, I wanted to mention Phospholutions, again, as Larry mentioned, was founded in 2016 after spinning some technology out of the university at Penn State that started to be worked on as early as the early 90s. Really, our focus and our founding mission is that we believe that more sustainable use of phosphate, both in terms of production and use on the farm field, is critical to meet a growing food demand. We've been set out on a mission to develop technologies that improve efficiency while also reducing the environmental impact and being sure that it provides value to both our growers and through the entire value chain in the fertilizer industry. We've now been backed by over 20 years of academic and on-farm trials. A little bit about us. After we took the technology out of the university to form Phospholutions, we've been very focused on taking a somewhat of an older technology that had more of an emphasis on more specialty-based crops and trying to bring this technology to general row crop production, not just here in the U.S., but also globally. That product development effort started as early as 2016 and quickly started to formalize into academic trials that started back in 2018, doing small plot research with university and other contract research partners. We quickly moved that technology and some final formulations on farm, testing to date over 200 trials with real growers across the U.S., including 14 states. In addition to that, we've been able to test the technology in over 5 countries around the world. And now in 2023, according to the spring, We've officially launched RhizoSorb to market. We are now selling an 839.0 based product that we'll talk about here briefly to ag retail for the U.S. farmer, primarily focused on row crops such as corn and soy. So let's switch gears a little bit and talk about phosphorus fertilizer. Quite a bit of opportunity from our perspective to improve the efficiency and ultimately drive more value and profitability at the farm gate. First off, what's important to note about conventional fertilizer use, specifically phosphate, is that as little as 10% is actually taken up by the crop in the year of application. This represents a huge opportunity for technologies to improve this. Really, there are a few key factors that lead to this inefficiency that we'll get into in a few slides. And this isn't a very efficient way to utilize this nutrient. This is the second largest nutrient needed for food production, yet quite a bit of it ends up being tied up in the soil in a form that becomes very unavailable to the plants over a long period of time, or ends up being lost into our waterways, which can cause all sorts of issues, including factors like algae growth leading to eutrophication. There's also a pretty large footprint from a greenhouse gas emission standpoint that comes from conventional phosphate use that needs to be addressed for the future. We know that this is an important nutrient for yield production, but having improved efficiency is really how we can drive higher profitability at the farm gate without over-applying nutrients or wasting them in the process. And then lastly, our mission is really to reduce costs associated with fertilizer use. There's a lot of wasted money that gets applied to the soil, specifically when it comes from phosphate. And there's a lot of room for opportunity to improve these per acre economics for row crops growers here in the U.S. We're going to spend just a second talking about phosphorus soil dynamics. This is kind of the 101 of how phosphorus interacts. It's quite a complex system in the soil when it relates to phosphate. Typically, farmers are applying conventional phosphates in the fall, typically in a dry granular fashion, sometimes in the spring. And then we additionally apply liquid applications, usually in furrow and a starter application early in the season. The reality is that when we apply these fertilizers, most typically our conventional sources or chemical sources are highly soluble in nature. And although that allows for those nutrients to be directly available instantaneously, the challenge there is that those applications don't always align with both soil dynamics and crop needs. We know that these products being highly soluble allow for the material to solubilize in the soil to be available, but what most don't realize is how quickly that phosphate fertilizer can be tied up. It happens almost immediately upon application. As soon as that fertilizer starts to solubilize, it is now susceptible to tying up in many different forms in the soil. Just some of these are represented here on the slide, where as phosphate becomes available in solution, it has the opportunity to tie up with organic matter. This can be either in the form of traditional organic matter, microbial, biomass, etc. And really this process of immobilization really does contribute to a lot of our phosphate to no longer be directly available in solution for plant uptake. There's also absorption that occurs onto soil particles, whether that be clay or other metal oxide-based particulates in the soil. We get essentially phosphate just tied to the surface of these materials that sometimes don't desorb at a rate that is consistent with plant needs. We can also precipitate phosphate in the soil. This is really when you have a bond that occurs between, say, calcium, iron, aluminum, where that phosphate essentially mineralizes out of solution to form a precipitate that becomes very difficult for the plant to end up extracting out of that precipitate over time. And then you have naturally soil-bound phosphorus existing naturally in the soil that is very, very tied up, that takes an extremely long time to ultimately break down and release into the soil. What's important to note here is that the only way a plant can take phosphate out of the soil is if it is directly dissolved in solution, which a very small percentage of overall total phosphorus in the soil is actually directly available in solution for plant uptake. What that leads to is either the phosphate that's in the soil solution, if there's too much, it's able to be leached, although that's typically not an issue with phosphate, as it's a very immobile nutrient, meaning it's very reactive, as we've just gone through, and likes to tie up with about everything in the soil. But more likely what happens is that most of what gets applied and gets dissolved in solution does get tied up in a way that won't be available throughout that individual growing season from application. So we'll talk a little bit about why the paradigm around storing or banking phosphate in the soil can still lead to quite an inefficiency, although we know we can extract some of that phosphate over time. It's not necessarily the most economical way to meet the fertility needs of the crop throughout the growing season. Phosphorus uptake is quite critical for, specifically here, we're looking at corn, quite critical throughout different stages of growth. We know that the corn crop requires some early on in the establishment, and as those stages go throughout the corn crop, we see that different levels are needed to accomplish different plant physiological growth patterns. The challenge with this is that a lot of our phosphates applied in one single application, and that season-long availability doesn't necessarily align with plant needs. Actually, the further we go throughout the season, usually the less available or that the less fertilizer is able to be released, even in those critical stages where quite a bit is needed. And just like nitrogen and sulfur, we need this throughout the entire season to maximize yields. And conventional sources simply aren't meeting that need the way they're used today. So phosphorus availability, it's a topic you hear quite a bit, especially when you're referencing either fertility programs or looking at soil tests. Availability is really around the soil's ability, theoretically, to release or replenish that soil solution as the crops are moving it. The challenge there is with our soil tests, we're really measuring the availability from a theoretical standpoint of what's theoretically extractable by the plant due to the different forms that phosphate may be available in that soil. The challenge is that we measure that availability, but we don't necessarily measure the ability for uptake. And so as an immobile nutrient in the soil and one that is easily tied up, phosphorus is something that certainly presents a challenge when it comes to current soil testing framework. And the three main ways that phosphate is taken up by the plant, there's really three main ways, but there's only one that really drives substantial uptake, and that's diffusion. So the root can directly intercept phosphate in the soil. Only about 3% of what exists in the soil naturally is going to actually come in contact with the root and be taken up directly by that root. Mass flow, although quite an important factor for nitrogen uptake, has very little impact on phosphate. And mass flow really references the soil water movement throughout that profile, bringing those more mobile nutrients to the root through the flow of water. Whereas in diffusion, which is really the process of moving through a concentration gradient, that is really where phosphate is typically driven into the plant. And so it happens pretty close to that rhizosphere. And you'll get kind of the focus here for our technology being called RhizoSorb. Play on words here, very focused on trying to absorb and desorb phosphate within that rhizosphere, which is the zone directly around the root. So it's important to note again, the movement of phosphate and the uptake is really driven by diffusion. As you can see, as we move from phosphate from a high concentration to a low, that plant can alter that environment around the root zone to acquire that phosphate into the plant. So agronomically, some of the challenges we experience with some of our conventional chemical fertilizer sources is that they get tied up very easily, almost immediately after application. That leaves very little to be plant available throughout the season, and it really relies on the soil's ability to replenish that phosphate over time. The challenge here is that we need phosphorus to be dissolved in solution for it actually to be taken up by the plant, yet a majority of it ends up being stored in this fixed pool. There is this active pool that happens in the soil, which is really referencing essentially the phosphate that's not directly in solution, but is in a form or bound in the soil in a way that can actually be released pretty quickly throughout the growing season. This is a pretty small portion of overall total phosphate in the soil, and this is overall really where we need to improve how phosphate can make its way and stay in an active pool, but not ultimately fixate in the soil to a point where it will not be released throughout the growing season. And like I mentioned on the soil test values, so typically as we report in on soil tests, what's important to note here is that really we're only providing an indication of what relative yield could look like if phosphate was not a yield-limiting nutrients in the soil. And those tests are pretty inaccurate in the sense that although they project what's theoretically extractable, there are some flaws in exactly how that message is being brought to the farmer versus what's really happening in the soil. And it's important to note that as you get to this optimal level and beyond, excess phosphate here in the U.S. does not typically drive an additional yield benefit. Plants tend to be luxury consumers of phosphate. So if they're sitting in a high P soil and they have the ability to extract more phosphate, they will. But that, again, does not necessarily directly result in a yield benefit. In some instances, literature has shown that actually decreases yields slightly in some situations. So again, it's all about trying to drive this optimal level. And certainly if you're in a low P environment, supplementing and building phosphate is critical. But we're going to show you how, this idea of what optimal really needs to be going forward. We need to consider more factors than just theoretical extractable phosphate. And again, it won't tell you how much the crop will actually take up. It'll just tell you what's theoretically available. And so this ends up leading to excess use. And that excess use can cause luxury consumption, or it can simply lead to environmental losses, neither of which are really the most economical use of those input dollars. One example that I always like to point towards is a study that was done really looking at the impact of phosphate concentrations on root development early on in the seedling stage. So what you're looking at here, essentially, across the top, the numbers here are essentially the concentration of phosphate that is being provided to the plant in a solution. And then you see the root architecture that forms from that use rate. And so typically we're taught in school, phosphate is very necessary to promote and develop roots. And although that's quite true from a plant physiological standpoint, phosphate is a critical component of root development. I think that there's some misconception around the amount of phosphate and how well the amount as it relates to root development occurs. And so what you see here is that as you start to get beyond a certain level of phosphate, you actually start to negatively impact root development. It's kind of a simple concept. It's very similar to watering. If you've ever had a house plant that you've killed because you've overwatered it, this idea of plants getting lazy. Why spend all this carbon and energy growing roots throughout the soil to acquire phosphate when you're simply drowning in it? And so that ends up leading to lower root densities, usually more shallow roots, and certainly not the root architecture that you can see in a more controlled, slightly lower concentration available directly to the plant. Other negative impacts of excessive phosphate use. Like I mentioned, root growth, you can typically see a reduction in mass as well as the overall size and root hair densities. You can see that sometimes excess phosphorus doesn't result in a higher yield, but in some instances it actually reduces the uptake and availability of other nutrients, which can cause even further detrimental impacts such as sulfur, copper, and zinc. And then in some instances, too many nutrients can lead to certain diseases in corn specifically. Things like stalk rot and ergot can be found. And just to highlight a little bit about the current phosphate management challenges, again, there's this misconception that fall broadcasting dry phosphate sources will be stored and it can all be released later when needed in season. There's a high percentage of what's applied that will be fixed in the soil and won't be released throughout the growing season that next year. Soil testing framework tends to lead us to over-application of phosphate. Farmers, we all kind of know that farmers tend to take an approach where, we certainly don't want to skimp out on nutrients. That is certainly an insurance policy to ensure yield. But I think we really need to think hard about the overall impact that has and how that may be contradicting what our objectives are here. Over-application does not always result in an increased yield. Rather, it lowers profitability and certainly doesn't benefit the environment. And again, to this point of soil testing, we really focus on measuring the theoretical quantity of extractable phosphate, rather than actually measuring the rate that phosphate can be released in the soil back into solution to replenish what the plant's removing. So we have to both be conscious of what's in the soil, but also how quickly that soil is able to release it to be able to provide that to the crop throughout the growing season. A piece that's currently missing from this current soil framework. I'm going to switch gears here a little bit onto our solution and why our technology, RhizoSorb, is really focused on giving plants phosphorus when they need it and making sure we store it in a much more accessible form when they don't. So to start off, RhizoSorb is very focused on phosphate today. We actually embed this technology directly upstream into the production process for conventional phosphate fertilizers. So MAP, DAP, TSP, we're working with large producers where they actually incorporate this material into the production process so that it becomes embedded into the granule. It's made the same way, shipped the same way, and applied the same way as traditional granular products. What we've been able to show throughout our research is being able to actually reduce use rates of P2O5 by as much as 50% and still show the same yields, same or greater yield in row crops such as corn and soybean. Our technology is not a biological. It's very much a soil chemistry-based approach, where essentially we are mimicking those interactions that I highlighted earlier on in the presentation around how phosphate can adsorb to the surface of various particles and allow for temporary storage on the surface of these particles to then be released at a later time. And again, we kind of mentioned a little bit about diffusion. Really, the similar approach is how the mode of action for RhizoSorb really works. So when phosphate is bound to the surface of RhizoSorb, it's not really going to release those nutrients unless that concentration gradient between that soil solution directly around the roots and the product changes. And typically what changes that concentration gradient is the uptake of nutrients. So every time a plant removes a unit of phosphate directly from the soil solution, that product, RhizoSorb in the soil, releases a unit back into solution to replenish what was ultimately taken up, creating this very consistent release that allows for us to store our conventional phosphate fertilizer in the soil to be available throughout the entire growing season. Like Larry mentioned, we're the only patented additive out there today that's truly embedded upstream into the production process, and really the only technology in the market that allows us to reduce P2O5 use by as much as 50% and still maintain yield. There's a huge sustainability benefit that comes with this product. We've shown out of some studies that we've been able to reduce runoff potential by as much as 58%. So this is phosphate running off the surface of the field. In addition to our 839.0 RhizoSorb product is about 51% less GHG emissions compared to traditional MAP use on a per acre basis. We also bring this technology to market under a cost reduction strategy. So rather than trying to benefit yield, we're really focused on trying to improve profitability for the farmer. So this is optimizing the application of phosphate to apply only as much as we need to make up for what the crop needs throughout the growing season, rather than over application to compensate for what's being fixed. We tend to provide a 10 to 15% cost savings to the grower on a per acre basis using our technology over traditional MAP. And then lastly, like I mentioned, 50% less phosphate, trying to preserve or even improve yield in certain situations. The technology is an 839.0 guaranteed analysis and is currently registered in the US and all states for sale. And we are currently selling this product through ag retail. And our product on the market today is derived from monoammonium phosphate. What's interesting to look at here as well is how this compares in terms of quality of the granules compared to traditional MAP. And essentially what you see here, two really important things to take away is that one, our technology is very similar in quality to traditional MAP. The only two differences is that we have a slightly higher crush strength, which means slightly less dust, and that we have actually about half the salt index as traditional MAP, which really adds benefit in certain regions where that salt toxicity can cause certainly some issues during establishment. I'd like to bring up a concept that may not be known to everyone on this audience today, and it's this idea of anionic exchange capacity. We talk a lot in the industry, especially when we talk about soil health, around cationic exchange capacity, or CEC. But really what's not brought up is AEC, which is the opposite end of the spectrum. It's interesting, our two largest nutrients that we apply for food production are phosphorus and nitrogen, and those two products are taken up actually in an anionic form by the plant. So really our focus and what our material does is it increases the exchange capacity for these anions, like phosphate, to be able to allow for more efficient adsorption, desorption to occur in the soil. What do I mean by adsorption, desorption? In the case of RhizoSorb, what I really mean is that during the production process, phosphoric acid is essentially adsorbed onto the surface of the material during production. And then as we apply that product to the field, rather than being directly soluble in water and being 100% released almost immediately after application, phosphate is actually desorbing off the surface of the product back into solution, again, as that chemical concentration gradient is driving that release based on plant uptake and needs rather than environmental conditions over time. In terms of solubility, it's interesting to see that as we incorporate RhizoSorb into the production process for conventional MAP, the more RhizoSorb you include, the more we alter the solubility. And what's really neat here is you see a nice balance between water solubility, which is more of the immediate release, versus citrate solubility, which is more of an extended release. Citrate solubility really refers to the ability for the root to exude acids, to break down or solubilize, certain chemistries. A lot of you may have heard of struvite being a product that is really 100% citrate soluble, and how that product is being used today is typically it's being used in conjunction with MAP because of the need for kind of more immediate release early in the season. With this technology, we kind of mimic that outcome in a much more economical way by being upstream into the production process. And again, also ties into how RhizoSorb is allowing for phosphate to be released throughout the entire growing season. You can see that here. This is a release study that was done with a RhizoSorb product compared to traditional MAP. Basically, as you can see, about 80% of all of MAP is released just 20 days into the season, and 100% of it's released not even halfway through the season. With RhizoSorb, as we get through the middle of that season, we still have a pretty good percentage of our total phosphate applied still available in a form and still releasing to the plant throughout that end of that growing season to really meet the critical needs throughout those stages of growth. And last thing I wanted to mention here was just how does this really work? A question we get pretty often is if you're using 50% less phosphate, how do you essentially fit into kind of conventional soil system approach of we need to bank it in the soil and build to a certain level before we can start to only apply what the crop is removing? We challenge that a bit, and I think the reason that framework exists today is because the sources we're using, so much of it gets fixed. When a lot more of what you're applying to the soil gets utilized actually by the plant or taken up by the plant rather than fixed, you can get away with applying a lot less. And it really comes down to that fact that as little as 10% of what we apply actually gets into the crop during that growing season. So what this graph is showing is essentially when we apply 50% less phosphate using RhizoSorb, we actually get a 3% increase in utilization rate over 100% of that soil fertility need being applied by MAP. Secondly, if you compare 100% of our product, 100% of the phosphate rate being applied through soil testing methods, we'll get about a 76% increase in utilization over the same amount of P2O5 being applied through MAP use. So again, when it's bound to RhizoSorb, utilization rates improve dramatically, which allows us to reduce overall application rates and save the grower some money while not letting that phosphate run off the field into the environment. And with that, I'd like to end kind of the technical portion of this call, and I'd like to switch it over to our VP of Sales, Craig Dick, to take us on a little bit of a journey through our trialing history to date.
Yeah, thanks, Hunter. So in our 2022 trials, this has been tested over a wide variety of soils with 93 trials over 12 states, primarily on corn, soybean, many application types, varying soil test types, which we'll get into. And these trials looked at specifically the grower's standard practice, which was whatever their soil test recommendation was, that was what they applied, compared to RhizoSorb 839.0 at a 50% P2O5 reduction. In those trials, we typically saw slightly better yield advantage. In 2022, we saw just slightly reduced yield, mainly due to drought conditions in many of the western states. But in Iowa, where we had plenty of moisture across 31 test sites using 50% less phosphate, we saw a 3.6 bushel advantage. In looking at many of those trials, this is the typical piano graph you're used to looking at. When we talked with each one of these trial cooperators, the growers all said, if we didn't see a +2% or a -2% yield advantage or disadvantage, we don't consider that your product. That is environmental noise. And so when we looked at anything down to a negative 2% yield, the majority of the trials were considered positive by the grower. When you looked at the even or better trials, still a majority of those trials were even or better. And then, of course, we did have some negative yield impacts, and typically those farms were highly correlated with those highly drought areas of Nebraska and South Dakota last year. We looked at all of our phosphorus levels in each of our trials, and we saw actually a pretty significant yield advantage in what we consider low phosphate soils, so under 20 parts per million. As you get in that optimal range of 20 to 40, or even the high range of 40 or higher, the yield advantages dropped off, and that is typical because typically once you're in that mid to high range of phosphate is no longer a yield limiting factor. And so by using RhizoSorb, we can apply phosphate much more judiciously, saving the grower quite a bit of money and still protecting or maintaining yields. So as we break down our trials further, looking at the corn trials with 50% less P, and again, RhizoSorb compared to the grower standard practice, the grower standard practice would be their full rate of MAP or DAP, depending on what their soil test requirement was and what product they're used to using. Again, we saw a slight yield advantage of 2.3 bushels with an 85% success rate over the 62 trial sources. Again, in Iowa, because of our concentrations of test sites, we broke that out. We actually saw in Iowa a little better advantage of 4.9 bushel advantage when you just look at corn. So pretty dramatic increase in yield. And again, using 50% P2O5, which would have given the grower somewhere between a 10 to 15% savings on a per acre basis. When we one of our field trials last fall in southern Indiana, actually the farmer called us and wanted us to come look at it. He wanted to know why the RhizoSorb trial with less P2O5 was actually greener. And so when we looked at yield was similar. Tissue tests were similar, and this is something we'll look at further, but it tends to lead us to believe that we are getting better phosphorus uptake late season in the plant from the soil, and meaning that we're not translocating phosphorus from old tissue to new tissue late in season. And again, the 50% saving or 50% P2O5 application with RhizoSorb gave the grower in that 10 to 15% per acre cost savings. One thing of note on all these trials, the rate of the phosphate applied in each of these trials was determined by the grower and varied from trial to trial. So it was set by the grower based off of their traditional practices, their soil test data, and so they set the rate that they felt comfortable that they normally would have used. And then our application with RhizoSorb is a 50% P2O5 reduction using RhizoSorb. Looking at just soybeans, when we broke out soybeans, again, saw a nice 1.6 bushel advantage with a 76% success rate. And again, the farmers determined their rate of P2O5 and then did a 50% P2O5 reduction combined with RhizoSorb. Many growers often ask us, and many agronomists often ask us, as we look at a 50% rate reduction, what happens over time? Will I maintain my soil test levels of phosphate with this rate reduction? And we are engaged in multi-year replicated studies at Penn State, looking at year-over-year trial data. And to date, we have seen no reduction in yield, no reduction in leaf tissue P levels, and no reduction in soil test levels. And when you, if you think back to the graph Hunter showed up, where we're getting 3% more utilization, what that actually equates to is the plant is actually utilizing the phosphate we're applying much more effectively, so it doesn't have to pull from the soil test pool. And so we are in our 5th year of study with Penn State. We'll continue to look at this, but everything in our research points to we are getting complete utilization versus soil tie-up. So again, looking at the grower benefits of using RhizoSorb 839.0 compared to traditional MAP or DAP, we have an increased phosphorus efficiency, which leads to greener plants, potentially higher yield. That potentially higher yield, layered with the 10 to 15% savings, can show a grower an ROI up to 20%. Again, we reduce nutrient tie-up. So this idea of we're going to apply excess phosphates into the soil bank in hopes of taking out that phosphorus later, that's not what we typically see in trial data. And lastly, with RhizoSorb, the grower doesn't have to change anything they do. RhizoSorb is built into the phosphate granule and can be applied any way they traditionally use MAP or DAP. The interesting thing is with RhizoSorb with a 50% P2O5 reduction, you're applying 33% less total product. So strip tillers and growers that are row placing their dry nutrients have really liked that savings. It allows them to put other nutrients, maybe micronutrients or a biological, into their blends and potentially drive more yield. One of the questions we get from many retailers is, why should I even give a cost savings? This is a new technology. It's a lot of work to sell it. And we've done market research. We've talked to nearly 100 growers. And while a third wouldn't need any savings, the majority of growers do expect a savings. And so by giving that around a 10% savings, 84% of growers would likely switch to RhizoSorb from a traditional MAP or DAP source. And lastly, for retailers, we constantly hear retailers, they don't want to sell, they don't mind selling less product, but they don't want to make less money. And obviously, with the way we go to market with RhizoSorb, we can actually improve retailer margins by up to 20% while reducing their operational expenses by 10%. And that's due to the decreased tons that they would handle by 33%. And again, though an agronomist, it's rare that they can come to the farm and offer a savings and potential yield advantage. And with RhizoSorb, they're able to do that. Lastly, the sustainability impact. Certainly, this is a foundational issue for our company. We believe in improving the sustainability of phosphorus, but it has to work agronomically and it has to work economically. And the team has worked hard to make sure that we can provide the agronomic and economic benefits. But on the sustainability impact side, we see a reduced runoff potential of 58% and leaching by 84%. So again, we're getting more utilization into the plant, less loss in the environment. As carbon credits become a bigger and bigger deal in this industry, we're providing up to a 51% decrease in carbon emissions. And we're actually seeing this third bullet point today. We've got our sales team out looking at trials all this week, and we're seeing larger root biomasses with 50% less P2O5. So, lots of great impacts coming on the environmental side here. Product availability. We work with many of the phosphate producers domestically and abroad to produce RhizoSorb at scale. It's currently available in totes or bulk, and we ship it from domestically available warehouses throughout the Midwest. We certainly, if somebody needs a larger quantity, can discuss barge or vessel quantities. And we do have a team already established here in the Midwest to work with your retailers and growers in your area to help you review this information we presented today and ensure that RhizoSorb is the right product to offer your growers. Lastly, I just want to add that next week we're sponsoring a webinar with the American Society of Agronomy on sustainable agronomy, and Dr. Chad Penn with the USDA ARS will be going more in depth in luxury phosphate consumption of plant, what impacts that has, and how his team is working to provide us as agronomists better tools to make better recommendations on phosphate applications. And with that, Larry, I think we can answer some of the questions that I've seen streaming in here.
Yes, indeed. Craig, thank you so much. And thank you, Hunter. Great presentation. And yeah, we do have several questions here from the audience. Hunter, why don't we start with you with this first question? Any chance you will develop this technology for liquid applications of 10-34-0?
Yeah, thanks, Larry. I think that obviously our focus today for RhizoSorb has been very much focused on dry granular applications, but we certainly do have formulation opportunities for this active ingredient and are pursuing opportunities for liquid applications in the future. But that will not be something available for the 2024 season.
Okay. Okay. Let's go to a question for you, Craig. How can retailers and growers both save money with RhizoSorb fertilizers?
That's a great question, Larry. So we offer RhizoSorb to the retailer at a 35% premium over MAP or DAP. Additionally, retailers will increase their margin that they normally get on a MAP or DAP product by approximately 50%. So that makes the product on a per ton basis more expensive than a MAP or DAP. But with the 50% P2O5 rate reduction on a per acre basis for the grower, they're going to save 10 to 15%, depending on whether they're using MAP or DAP. And so we have a number of calculators that are built that we would be happy to walk through on a one-on-one basis with anybody who wants more information. We can walk through a very detailed example of how that works. But, essentially, we've engineered this to offer the grower cost savings. We know the retailer is going to sell less product, but it's a new technology, so they need to make more on a per ton basis, and we've certainly done that.
Okay, thank you, Craig. All right, Hunter, let's question back to you for another question. Is embedding superior to a polymer coat? Excuse me.
Yeah, so Larry, I think that the difference with our technology is that our release of phosphate into the soil system is not driven by the same environmental conditions that drive polymer release. So what I mean by that is that, rather than coating a granule with a polymer that really is driven, a certain level of thickness is applied so that thickness is extending release based on time, temperature, and moisture. We're really focused on storing nutrients or impregnating our material with phosphate so that it is releasing, but only releasing based on plant needs rather than environmental conditions.
Okay. Thank you. Craig, coming back to you. Is there any difference in effectiveness of RhizoSorb if it's applied in spring versus the fall?
In our trial data, we have not seen a difference in effectiveness versus spring or fall. And maybe I'll lean on Hunter a little bit for a little more color into that, but I have not seen that in our data, that there's any difference.
Yeah.
Okay.
So I think the reality here, Larry and Craig, is that, spring fall applications, I think that we know that in most instances, from a broadcast standpoint, fall tends to be a more convenient time to apply. And I think with conventional fertilizers, you'll likely see some difference in efficiency between fall and spring application. And that's really due to the fact that, as we apply it closer to planting, obviously it's going to be releasing nutrients pretty quickly as a conventional source. And so it's closer to when the plant is actually going to be using them, rather than giving all of that time throughout the winter and early spring to be fixed. But when you use an amendment like RhizoSorb in that granule, and you're preventing fixation, the difference between a fall and spring application in terms of efficiency starts to minimize.
Okay. Thank you. Staying with you, Hunter, has there been any work done by using same P rate from RhizoSorb as MAP/DAP? Notice even better P2O5 efficiency?
Yes. The reality is that in some of our trials, actually most of our trials, when we start to apply 100% of the P2O5 rate driven by soil testing recommendations, we still don't see a substantial yield increase over traditional MAP use at that same rate. And the reason being is that although we may be getting higher tissue testing results, it doesn't always correlate to higher yields. And I think that, again, back to the critical takeaway for this webinar is that, look, too much phosphate doesn't mean more yield. What we need to do is get just the right amount into the plant, and that means better use efficiency for what's being applied. And so to answer the question very simply, just because we apply 100% of that recommendation with RhizoSorb, if phosphorus is not a yield-limiting nutrient, you will not see a yield gain from over-applying our product either.
Okay. Thank you, Hunter. Staying with you here. How much P were you actually applying?
So how we design our field trials are we go based off of traditional soil testing methods. So that soil testing method will vary depending on the region that we're focused on the trial. This is driven by university recommendations. Those soil tests will be taken in the beginning of the season or whenever it's kind of standard for the grower. And those soil testing recommendations will derive a P2O5 recommendation for a yield target. We then consider that the 100% P rate for that trial. And so we'll apply that phosphate rate through the use of MAP or DAP fertilizer. And then we'll go and reduce that overall application rate on a P2O5 basis by 50% and apply that through the use of RhizoSorb. And so, again, each trial varies in terms of the total amount. It can range from 60 to 200 pounds of MAP in this instance, and then about a third less is what we end up applying in terms of total volume of RhizoSorb per acre.
Okay. Thanks, Hunter. Craig, question for you, sir. Trials were, I think words misspelled here, placed in low or trials were planted in low or high P content fields. That's a question, yeah. I think. But I think it's some of the words were spelled wrong there.
So this is a common question we get from ag retailers and growers as well. In all of our farm trials, the phosphate levels varied, and as you can see from here on the screen, hopefully on my slide, that we group those in ranges from under 20 ppm Bray to over 40 ppm Bray. And back to Hunter's answer our question on 100% P, we actually saw better yield in where we were actually using less phosphate with RhizoSorb. So again, to answer the question, the P205 or the phosphate levels on the farm fields varied, and so we've got a lot of different data over a wide range of soil phosphate levels, and certainly can dive deeper into that if somebody would like to follow up with us after this webinar.
All right. Thank you, Craig. All right, Hunter, coming back to you. How can you reduce phosphate by 50% and not impact soil test levels?
Larry, it all comes down to utilization rate. So if we get a higher utilization rate out of what we apply, we don't need to apply as much. And so again, I think Craig mentioned this earlier in the presentation. If you're able to get that higher utilization rate, essentially we don't start drawing as much out of the soil phosphorus pool. If we can rely on applying only what the crop is truly going to be removing from the soil system, you don't see a depletion in the soil testing levels the following year.
Okay. Thank you, Hunter. Craig, coming back to you. How do the handling properties of RhizoSorb compare to traditional MAP fertilizers?
Almost identical. It's effectively just as hard as MAP. It stacks the same as MAP or DAP. Crush strength is similar. Again, probably the biggest benefit is it allows retailers to handle 33% less volume, therefore freeing up storage space for other products they may want to carry. And then lastly, for those growers that are row placing phosphates with their seed, like with wheat or canola, that reduction in salt index is pretty substantial. So, to wrap it up, it's just like MAP, but maybe slightly better.
Okay. Thank you, Craig. Hunter, back to you, sir. Have you tested this both in conventional and no-till frameworks? I also wonder, does this have an effect on the microbial communities?
Great question. In terms of conventional versus no-till, it's actually been something that has been tested in both. And although we didn't break out our aggregate trials into that, we certainly do have trial experience in both systems. I think what we find in no-till systems, obviously, if we're able to strip till or band in any which way, we're going to naturally get better product efficiency due to better placement than broadcast. But really, again, the value from an agronomic standpoint remains really the same in kind of all systems over conventional MAP use. In terms of the question around microbiome, it's an interesting one. It's something that we're certainly exploring in more detail. I mean, being a soil chemistry-based approach and reducing overall chemical use of fertilizer, at least the hypothesis is that we would naturally benefit the microbiome in that sense. But really where I think our interest lies even more is how the microbiome can complement kind of the mode of action or the use of our technology. I always like to use the analogy, Larry, of the crowbar and the sponge. Our technology, RhizoSorb, acts as a really great sponge to essentially soak up and store phosphate. The challenge is there's a lot of phosphate naturally in the soil. And for us, our technology, to be fully transparent, is not really, able to be that crowbar to essentially unlock phosphorus naturally in the soil, but rather keep what we apply in a more plant-accessible form. So we see that the microbiome plays an important role in being that crowbar to strip more phosphate loose. And if it is stripped and directly available in solution, we know that RhizoSorb can continue to buffer phosphate in the soil system over time.
Okay, thanks, Hunter. Questions keep coming in here. Craig, coming back to you, sir. High P levels are a problem in the Salinas River in California. I want to know if you have a California rep out there.
Not currently. I could certainly I covered all the areas that we don't currently have a rep in, and within a couple of weeks we'll be welcoming a technical agronomist to the team with quite a bit of California experience. So
awesome.
Whoever asked the question would love to talk to them in more detail.
Okay, great. Hunter, coming back to you, can we use RhizoSorb on citrus plants like oranges for 10-year trees? What is the dose?
It's a good question, Larry. I think that in terms of citrus plants, I mean, look, phosphates, orthophosphate, when it's bound to the surface of RhizoSorb, it's not necessarily driven by a particular cropping system. I think that the transparent answer here is that we haven't really done tests in citrus, and something would be very open to trialing, and I think that would help us nail down more of that use rate question.
Okay. Staying with you here, Hunter. When is the most critical time of the corn plant's life cycle for P uptake?
Yeah, so Larry, there are a few different critical timelines in the life cycle for plant uptake. Typically early on, when we're establishing early on in that season, kind of post use of that seed's natural reserve. That's why we typically apply starter. We do see that there's a big uptick throughout some of the vegetative growth, but really as soon as we hit that reproductive stage, phosphorus is a critical component of both kernel development as well as tasseling, and then kind of as we form that and start to that crop starts to dry out, we start to see that decrease again. So really, there's probably 2 to 3 key stages where quite a bit of phosphate is needed to be available. And like we've mentioned throughout this presentation, the challenge with conventional sources are later in the season, the less is available. And that really is kind of opposite of what the plant's needs really are.
Okay. Thank you. All right. Craig, coming back to you. Has any research been done into specialty crops? And if so, what crops?
Yeah, great question. Again, the technology was originally used in horticulture. For us, in our trials with specialty crops, we currently don't have any specialty crops. We've had a lot of interest from many specialty crop growers since we've launched the technology, and we'll be establishing more specialty crop trials this fall. So if you're a specialty crop grower or service specialty crops, we'd love to talk with you and help you establish trials in your area.
Okay. Thanks, Craig. Hunter, coming back to you. How does the usage of RhizoSorb affect the mineral profile of the crop, especially in regards to heavy metals?
Sure. So the interesting part about RhizoSorb, like I mentioned before, we're trying to really mimic natural soil chemistry. So our product is composed of a blend of activated metal oxides. These metal oxides are really naturally occurring in the soil already. We've essentially established a technology that we have the ability to mine, refine, and process these metal oxides in a form that really optimize their ability to bind and release phosphate. In terms of how does this affect the soil, the physical properties, heavy metal, there is absolutely no contribution to heavy metals in this instance. We've tested that ad nauseum. In addition to that, we actually see a somewhat of a reduction in overall uptake of certain metals like aluminum, as our technology not only has a high anionic exchange capacity, but does have a slight cationic affinity as well. So we can certainly tie up and bind some of those things, although that's not a claim we take to market. And in terms of the profile, it really just becomes naturally part of the soil, mineralogy. It's just it's another mineral-based material that's applied at an extremely low rate from an active ingredient standpoint compared to the total volume of these metal oxides existing in the soil.
Okay. Thanks, Hunter. We have one final question for Craig. RhizoSorb costs. What does RhizoSorb cost in comparison to MAP and DAP?
Yeah, so a grower can expect to spend 10 to 15% less on a per acre basis when using RhizoSorb compared to MAP or DAP. Again, we do sell RhizoSorb to retail at a 35% premium over MAP and DAP prices, and essentially based off of current trading prices. And so that can vary from day to day. But again, the important thing is not a per ton price, but what does it actually cost the grower on a per acre basis. And the growers that we are working with today are very excited about that 10 to 15% cost savings on a per acre basis.
Okay, thanks, Craig. Well, that about does it for the questions. We got them all answered. Thank you, gentlemen. Couple of housekeeping things here before we say goodbye to our audience. I just want to thank everybody once again for attending the webinar, and I want to thank Phospholutions for presenting it, and thanks to Hunter Swisher and Craig Dick for providing an excellent overview on this topic. And also, as mentioned earlier, you can receive your CEU credit by scanning the QR code that is currently on your screen with your mobile device. And once scanned, the app will automatically sign you in. So it's on the screen right now. And if you would like to watch the webinar on demand or just check on different parts of it, it will be archived and available at the same link you used to get on today. You'll also receive a reminder of the archive by email tomorrow that will have the link in it. Thank you again for joining us today. We appreciate it. Have a great rest of the week.